Hi, my name is Zhihan Guo. I'm a third-year PhD student working with Professor Xiangyao Yu. Today, I'm going to present our work on reducing contention of hotspots by violating two-phase locking. This is joint work with my co-authors from UW Medicine and Microsoft Research. Having a hotspot would cause a lot of contention, which leads to limited parallelism. Hotspots are some data items that are so frequently updated, which becomes the locking bottlenecks. There are some common types of hotspots. One is summary information, such as the amount of money in a bank branch, since every debit and credit transactions needs to update that value. And another type is the next serial number to be sequentially assigned, such as the order number. There are also examples like the popular inventory items that almost every order involves, such as popular items that people would snap up on Black Friday. Next, we show an example of how hotspots cause much contention in conventional concurrence control protocols, such as two-phase locking. For example, we have a transaction T1 trying to update a hotspot A at the beginning of its execution. When there are two other transactions, T2 and T3, also trying to update the hotspot A at the same time, assuming we're using two-phase locking, T2 have to wait and cannot update until the T1 commits. And T3 also needs to wait until T1 and T2 finish the entire execution. Though they only conflict on a single data item, they enjoy no parallelism and were executed in a serialized fashion. It is similar in optimistic concurrence control. Instead of blocking, conflicting transactions will fail the validation at the commit time and keep aborting. Ideally, we want a concurrence control protocol to serialize transactions only for the duration of the hotspots, but executes the rest of the transactions in parallel. If updating the hotspot only takes up a small fraction of the transaction's total runtime, such an ideal protocol can improve performance substantially. Thus, we propose a new concurrence control protocol called Bamboo, trying to achieve such ideal case. However, in pessimistic concurrence control, this would violate two-phase locking, which brings up a few challenges. Next, we'll discuss what are the challenges and how we solve it. There are two major challenges we're going to talk about. One is maintaining serializability, and the other is cascading aborts. Let's start with the first one. Here in the figure, we showed previously the ideal case. In order to achieve this, it requires T1 to release its lock after updating A, and so that T2 can access A before T1 commits. This clearly violates the two-phase rule, and as a consequence, it may violate the serializability as well. For example, if we allow T2 to read T1's data before T1 commits, and then T1 aborts, and committing T2 will be incorrect. Thus, the first thing we need to do is to track such dependency due to reading uncommitted data. Here, to differentiate a release and an early release before commit, we introduce the notion called retire. In the normal case, where we release the lock after commit, we can completely forget anything about the transaction. And in cases we want to release the lock earlier, but we still need to keep track of who has not committed yet. We issue retire instead of release. Note that retire is just an extra API you can leverage compared to the conventional 2PL. And not calling retire will just fall back to the baseline. And it is totally fine that a transaction can have some locks retired and some other locks not retired, and it won't affect the correctness. And we have more discussion on how and when to retire in the paper. Once we keep such dependencies due to early release, we need to enforce transactions involving dependencies that must abort if any ancestor aborts and cannot commit if any ancestor has not committed yet. And Bamboo can actually satisfy both requirements through how we keep retired lock holders. And you can check our paper for more details. Note that Bamboo is provably correct, and the formal proof is in the extended version of our paper. As we just discussed in the previous slide, that a transaction must abort if any ancestor aborts. And so the problem is when there is a long dependency chain, such as shown here, if T1 aborts, then T2 and T3 need to abort as well, which we call cascading aborts. And this is our second challenge. As the name cascading may indicate, cascading aborts is problematic. It causes waste of work and performance degradation to some extent. So how do we handle this? There are three possible cases that an abort can happen. The first is user-initiated aborts, and we have no control of that actually. But the other two are aborts caused by deadlock prevention algorithms, such as no wait, wait die, won't wait. And there are aborts due to reading uncommitted data. And actually, we have several optimizations that can reduce the chances of aborts due to deadlock prevention algorithm. And Bamboo is actually based on one of the deadlock prevention algorithm, which is called won't wait. And won't wait prevent deadlocks by assigning priorities to transactions. And in Bamboo, we can actually assign these priorities only when a transaction encounters its first conflict. Thus, most transactions will not abort on its first conflict in the result. And the second optimization, we actually create local copies on write so that we can keep multiple in-flight versions to avoid aborts caused by read after write conflict. For example, when a high priority read comes in and tries to kill low priority transactions with retired locks because it needs to avoid deadlock. And in this case, it can find one of the on-flight versions to read so that no retired transactions will be killed. And the next optimization is to not retire when the benefit is limited. As mentioned earlier, you can control which access you want to retire for every transaction. And when a transaction find itself is almost done with the execution, it can decide not to retire the locks anymore, as it won't take too long for others to wait even if they don't retire. There also have more opportunities that people can exploit from this feature. For example, people can only enable the retire mechanism on hot data. So the last thing to mention is that intuitively, casting aborts may not be too bad in cases where the chances of having deadlock are rarer than the chances having a conflict. And we have a theoretical analysis on this in the paper. You can check section 4 for that. And here we'll just show some empirical results. We run a set of synthetic workload, and in each of the workloads, all transactions are of the same type. They all access two hotspots. In a set of the workloads, we always fix the first hotspot access at the beginning of the transaction and changing when to access the second hotspot in different workloads. And for example, when the distance between the two hotspots is 0, it corresponds to workload like this, where all transactions access the two hotspots at the beginning of the execution. And in this case, we would expect less chances of having deadlocks and aborts in Bamboo. And moving along the axis, we move the axis to the second hotspot gradually from the beginning to the end of the transaction. And in the process, the chances of aborts due to deadlocks increase as well. And as you can see in the runtime analysis, Baseline won't wait, spend most of its time on waiting for logs, while Bamboo spend little time on waiting for logs, but it spend increasing amount of time on boards as the distance between two hotspots increase. And from the experiments, we can see that even when there are a lot of time spent on boards, it actually will it's actually less likely to cancel out all the benefits from reduced waiting in Bamboo. And so it still have improvements against the baseline won't wait. And notice that when their distance is increased to 1, the throughput improvement jumps back. And this is due to the optimization we just talked about, where a transaction will not retire a lock when there are limited benefits. And so we can see there no longer have that many aborts as we had before. Instead, we have more waiting here. And you can also check our paper for the casting abort analysis on more stress tests. So how much benefit can Bamboo bring us in the ideal scenario? We perform a simple synthetic test, such as shown in the ideal case where every transaction accesses the same hotspot at the beginning of the execution. And we can see from the figure on the right that as the length of the transaction increase, the speed up of Bamboo over the baseline in throughput increase as well. And when the time for accessing a hotspot takes up nearly just 1/64th of the total runtime, the speed up of Bamboo can be nearly 20x with 32 threads. Next, we evaluate Bamboo on a more realistic TPCC workload. Here we run the experiment in 2 setups. In the stored procedure mode, benchmark transactions are compiled with the database and everything is running locally on a single machine. And in the interactive mode, we have 2 servers. One is transaction client that sends out requests through gRPC. And the other is database server that handles its gRPC requests to perform read or writes. And in this setup, the network latency became the major bottleneck. And we run TPCC workload with one warehouse. And note that in this workload, 1% of the new order transactions are chosen at random to simulate user-initiated words. And as shown in the result, even with user-initiated words, Bamboo can obtain up to 2x improvements against wound weight in both stored procedure mode and interactive mode, and it outperforms other 2PL variants and OCC protocols. We also have experiments showing results on different settings, and these settings include large number of threads up to 120 core, and a large data set on YCSB, as well as tests on long read-only transactions. And most of the time, Bamboo outperforms the baseline and never underperforms the baseline due to cascading aborts. Please check our paper for more details. In conclusion, we propose Bamboo which is compatible with traditional two-phase locking, but allow reading uncommitted data to reduce contention. And we perform extensive theoretical and empirical analysis on cascading boards. We also did evaluations on various workloads. It showed that Bamboo can obtain up to 3x over baseline on high contention TPCC and up to 20x over baseline on the ideal scenario. And thanks for listening, and feel free to ask any questions. Thank you.